Good evening, students. Once again, I welcome you all to my channel. Now, I'm going to discuss another topic in digital logic circuits, that is multiplexers and demultiplexers. Basically, a multiplexer is a combinational logic circuit that selects binary information from one of many input lines and directs it to a single output line. The selection of particular input line is controlled by a set of selection lines. Here, this multiplexer have multiple inputs with only one output. At any instant of time, with the help of selection lines, we'll select one of the input. Whatever the binary information that input have, that is simply transferred to the output. Because of this, multiplexer is called data selector. There are 2 power n input lines and n selection lines whose bit combination determines which input is selected. That means if you consider a multiplexer which may have 2 power n number of inputs, as usually one output was present, then the number of selection lines that multiplexer has n selection lines. Based on the bit combination present on selection lines, we will select one of the input of multiplexer. We have 2 power n number of input lines. See here, friends, this is a multiplexer block diagram. That is, it has 2 power n inputs, one output. My input of I0, I1, and so on, I 2 power n minus 1. That means the total number of inputs, this multiplexer has 2 power n inputs. Y is an output. And number of selection lines here is n selection lines, because the selection lines start from S0 and it is ends with Sn minus 1. The total number of selection lines are n selection lines. Sometimes the multiplexer we can also represent like this. And we can call this multiplexer is 2 power n by 1 multiplexer. That means 2 power n input this multiplexer has, one output with the n selection inputs. Based on the bit combination present on these selection lines, we select one of these inputs. That input is directly connected to the output. Because of this reason, the multiplexers are also called data selector. Coming to the first simplest multiplexer is a 2 by 1 multiplexer. Its block diagram is this. 2 by 1 multiplexer or 2 to 1 multiplexer, it means it has 2 inputs and 1 output. My 2 inputs are I0 and I1 and output is Y. The number of selection lines for this multiplexer is only 1 selection line, because here my number of inputs are 2 power 1. Generally, the representation of multiplexer is 2 power n by 1, where 2 power n is number of inputs and n is an output. If you consider that logic, for this multiplexer has 2 power 1 inputs with 1 output. That means it has 2 inputs and 1 selection line S. Coming to the truth table of this multiplexer is the selection lines we are using for selection of these inputs. So I take it as selection line S. One selection lines, I have only 2 possibilities, that is S is equal to 0 as well as S is equal to 1. Based on the combination present on the selection line, one of these 2 inputs are directed to output Y. So Y is equal to I0. When it was happened is this selection line S is equal to 0. Once S is equal to 1, I1 is directed to Y. Whatever the I0 and I1, it may be 0 or 1. Once the corresponding input was selected, it is simply directed to the output of the multiplexer Y. That's why here I didn't write a constant value 0 or 1. Instead of that, I write the input variable names, that is I0 and I1. If I go and write an output expression with SOP form, then I can written as like this: S bar and I0 plus S1 I1. That means whenever S value is 0, Y is equal to I0. So that I take it as S bar I0. If I0 is 0, here 0 comes. If I0 is 1, here 1 comes. If S is equal to 1, that means S I1. Whatever I1 we have, that is reaches to an output. This is a simple truth table of 2 to 1 multiplexer or 2 by 1 multiplexer. Coming to the logic diagram of it, this can be implemented with two input AND gates. That is, these two are the two input AND gates. For each one have one input is I0, and for second AND gate one input is I1. But the second input for these two AND gates is our selection line. Let it be this is the first AND gate, which may have one input is I0. Second input should be S bar. That means the selection line value is equal to 0. So that it is given to a NOT gate. NOT gate output becomes S bar or S prime. So the output of this AND gate is I0 dot S prime or S bar. Coming to the second AND gate, one input is I1, the second input is as usual S. So the output of this AND gate is Si1. Now these two are given to an OR gate. OR gate output is Y. So Y is equal to S bar I0 or S prime I0 plus S1, Si1. So this is simple logic diagram, truth table and block diagram of 2 to 1 multiplexer or 2 by 1 multiplexer. Next come to a 4 to 1 multiplexer or 4 by 1 multiplexer. So 4 to 1 multiplexer, if you write in generalized form, it is 2 square by 1 multiplexer. That means the number of inputs are 4 and the number of selection lines are 2. But we have only one output. Again, based on the combinations present on the selection lines, we select one of these 4 inputs to output Y. 2 selection lines, the number of possible combinations are 4. Each combination is used to select one of these 4 inputs of your 4 to 1 multiplexer or 4 by 1 multiplexer. Coming to the truth table part of it, S1 and S0 are the selection lines. These are the 4 possible cases. If S1, S0 both are 0, 0, I0 was select. That means what are the value that should be present on this I0? That is directed to Y. If S1, S0 is 0, 1, I1 was selects. That instant, whatever the value here we have, that is transferred to Y. Next, S1, S0 is 1, 0, I2 was selects. So whatever the value here that was present, that is directed to Y. And last combination is S1, S0 is equal to 0, 1, 1. Then I3 was selects, that was directed to Y. Now if I go and write the output expression Y for this 4 to 1 multiplexer is S1 bar, S0 bar, I0, because I'm going to write a product term. Product term in the sense min term. Min term value is always 1. The time we consider variable values are, it is 0, we take it as a complement. It is 1, we take it as uncomplement. By using that logic, here Y is equal to S1 bar, S0 bar, I0 plus S1 bar, S0, I1 plus S1, S0 bar, I2 plus S1, S0, I3. This is your simplified output expression of 4 to 1 multiplexer. If you go and realize it in terms of logic gates, I have a 4 product terms, so I need 4 AND gates. Each product term have a 3 variables, so that I took a 3 input AND gates. So this is the first AND gate. One input is I naught, and second input is S1 bar, and third one is S naught bar. So let it be, friends, take it as this is the selection lines S1 and S naught. For some of the terms, these are uncomplemented form, and for some of them, these are complemented form. For the case of first AND gate, these two should be in complement, so that the output of this NOT gate we consider as S1 bar here, and the output of this NOT gate is considered as S0 bar. These two are given to 2 and 3 inputs of your AND gate 1. Then the output of this one is I0, S1 bar, S0 bar. Similarly, for second product term, this is an AND gate I was used, because one of the input for this AND gate is I1, and next two more inputs are S1 bar, that is this is an S1 bar, and another one is S0. So S0 is directly connected here. So the output of this AND gate is S1 bar, S0, I1. Then coming to for the third product term, this is an AND gate was used. For this inputs are I2, S1, and then S0 bar. Similarly, for last gate, the inputs are S1, S0, I3. So this is an S1, this is an S0, and this is I3. All these product terms are ORing together, so that the outputs of these AND gates are given to an OR gate. The OR gate output is a Y, which is equivalent to this. This is a 4-to-1 multiplexer or 4-by-1 multiplexer. Then coming to 8-by-1 multiplexer or 8-to-1 multiplexer. That means it has 8 inputs, 1 output. Then the number of selection lines here is 3, because if you write 8 in terms of 2 powers, it is 2 cube by 1 or 2 cube to 1 multiplexer. So number of selection lines for this multiplexer is 3. Those are S2, S1, S1. Again, based on the combination present on these selection lines, we select the inputs of this multiplexer from I0 to I7. The truth table of this multiplexer is like this. It is similar to previous case. S2, S1, S0 all are zeros. I0 was selects. That I0 is directed to output of O. Next combination on selection lines is 0, 0, 1. That time I1 was selects. That was directed to output O. The selection lines combination is 0, 1, 0. Then I2 was selects. I2 is directed to O. Next combination is 0, 1, 1. I3 was selects. I3 is directed to output O. Next combination is 1, 0, 0. I4 was selects. It is directed to output O. Next one is 1, 1. That is I5 was selects. Then it was directed to O. Next, the combination on selection lines is 1, 1, 0. Then I6 was selects. That was directed to O. And the last combination on selection lines is 1, 1, 1. I7 was selects. It was directed to O. That is an output. Now, if you go and realize it, your output function Y is equal to S2 bar, S1 bar, S0 bar, I0. See here, friends, this is that first AND gate is. This is an I1, and this is a S2 bar, and this is S1 bar, and this is S0 bar. And the second one is S2 bar, S1 bar, S0, and I1. So this is an I1, S2 bar, S1 bar, and then S0. Like that, this is the last AND gate, which can produce a term S2, S1, S0, I7. So this is an I7 input, and this is a S2 input, and this is a S1 input, and then this is S0 input. All these AND gate outputs are ORing together, so that here I was used 8 input OR gate. So OR gate output will act as an output of multiplexer. So that's the cases. The next thing is implementation of higher order multiplexers by using lower order multiplexer. Here I consider an example is 4 by 1 multiplexer implementation that I was doing with the help of 2 by 1 multiplexers. We know that 2 by 1 multiplexer has 2 inputs and 1 output. See here, for my destination multiplexer has a 4 inputs, so that at input stage, I'll go and take two 2 by 1 multiplexers. The first 2 by 1 multiplexer consider not I1, and the second multiplexer have an input I2 and I3. And these two multiplexed output have these two are the outputs of multiplexers. These are given to the input of another a 2 by 1 multiplexer which was present and output at. And see here, friends. Sorry. See here, friends. If you go and take a 4 by 1 multiplexer, if you consider a truth table, so see here. So this is, for this case, the selection line S0. S0 is 0, I0 was selects. S0 is 1, I1 was selects. Again, S0 0, I2 selects. S0 is equal to 1, I3 selects. You just should remember. But coming to S1 case, it continuously 0 for I0 and I1. It is 1 for I2 and I3. So here I was using a same logic. For I0, I1, I2, I3, I was using S0 as a selection lines. Because S0 is equal to 0 for I0 selection as well as I2 selection. S0 is 1 for I1 selection as well as I3 selection. Now these two things are given to the inputs of your output multiplexer 2 by 1. Here S1 is equal to 0. This input was selects, which is an output of this multiplexer. S1 is 0 for input I0 and I1. So that these inputs are reaches to output Y like this. Like this. If S1 is equal to 1, it selects I2 and I3. That means this multiplexer output was selects. So I2 is reaches to output like this, or I3 was reaches to output like this. So like this, I can implement higher order multiplexers by using lower order multiplexers. This type of structure is called MUX tree structure. Next, in a similar way, implementation of 8 by 1 multiplexer. So 8 by 1 multiplexer has an 8 inputs, I0 to I7, 3 selection lines. If you refer 8 by 1 multiplexer, the truth table, S1, S0, 0, 0 case for I0 and I4. It is 0, 1 case for I1, I5. It is 1, 0 case for I2 and I6, and 1, 1 for I3 and I7. I use that logic so that this is my first multiplexer. So I0, I1, I2, I3 are the inputs. This is my second 4 by 1 MUX. I4, I5, I6, I7 are the inputs. So these are the least significant two selection lines are combinedly connected to both the multiplexers. Then the output of these two multiplexers are given to a 2 by 1 multiplexer. That 2 by 1 multiplexer have a selection line which is the higher order selection lines of our 8 by 1 multiplexer S2. S2 is equal to 0. Then we select input I0 to I3. Here this is a 0th input. And S2 is equal to 1. We select the inputs from I4 to I7. That means this multiplexer was selects. So based on this selection lines combination, out of these 8 outputs, one out of these 8 inputs, one input is reaches to output Y. So this is 8 by 1 multiplexer. In a similar way, 16 by 1 multiplexer for realization, I use two 8 by 1 multiplexers. For 4 by 1 multiplexer or 4 to 1 multiplexer, I have a 16 inputs, 4 selection lines, 1 output. 4 selection lines are S3, S2, S1, S0. And one output is Y, and your inputs are I0 to I15. So for this first multiplexer, I was connect I0 to I7 inputs. For second multiplexer, I was connect I8 to I15. So based on the combination on S2, S1, S0, I select these inputs and these are reaches to the last stage 2 by 1 mux. The 2 by 1 mux have a selection line is S3. S3 is 0 for all these 8 inputs. S3 is 1 for all these another 8 inputs. So based on S3 value, S3 is 0, I will select the output of this mux. S3 is equal to 1, I will select the output of this mux. Like that, the output reaches these inputs I0 to I15. The same 16 by 1 mux are realized by using 4 by 1 multiplexer. So for 4 by 1 multiplexer, there are 4 inputs with the 2 selection lines, 1 output. If you refer 4 selection lines, S3, S2, S1, S0, S1, S0 continuously changing from 0, 0, 0, 1, 1, 0, 1. So for first multiplexer, this is, so that time this have an inputs I0 to I3. This is a second multiplexer. My inputs from I4 to I7. This is the third I8 to I11. This is the last I12 to I15. For all these, the multiplexers are concurrently or parallelly connected selection lines are S1, S0. If these are 0, 0, in this multiplexer, I0 was selected. Here I4 was selected. Here I8 was selected. And here I12 was selected. If it is 0, 1, here I1, I5, I9, I13. 1, 0, I2, I6, I10, I14. 1, 1, I3, I7, I11, I15. So by using these selection lines, we select these inputs. Now the outputs of these multiplexers are given to another 4 by 1 mux. For this 4 by 1 mux, the selection lines are S3, S2. S3, S2 is 0 for I0 to I3 case, that is 4 zeros to 0011. S3, S2, 0, 1 for I4 to I7. S3, S2 are 1, 0 for I8 to I11. These two are 1, 1 for I12 to I15. So 0th input, 1 input, 2 input, 3 input. Based on the combination present on this, these multiplexers outputs are reaches to the output F. So like this, I can realize higher order multiplexers by using lower order multiplexer. Now, another important problem on multiplexer is implementation of Boolean functions by using multiplexer. In that process, I'm going to design a full adder circuit by using 8 by 1 multiplexer. We know that a full adder is an adder circuit or a combinational logic circuit which can add 3 binary bits at a time, and it can produce sum and carry are the outputs. We know this. So for sum output, so sum is 1 for 1, 2, 4, and 7. So I written as sum expression is S is equal to sigma m of 1, 2, 4, 7. Similarly, carry is 1 for 3, 5, 6, 7. So C is equal to sigma m of 3, 5, 6, 7. Now I would like to select a multiplexer. Which number of selection lines is equal to the number of variables present in the given Boolean function. Here I was implementing full adder. Full adder have a 3 inputs so that my selection lines for multiplexer is 3 selection lines. Each multiplexer here is can produce only one output, so that one multiplexer can produce some output, another multiplexer can produce carry output C. See here friends, these are the 8 by 1 mux. I should go and define what my inputs are. Previously here we have I0 to I7. Instead of that, here we are going to place the constant value 0 to 1, 0 or 1. If you coming to the sum case, 1 output is 1. For min term 2 is 1, 4 is 1, 7 is 1. So that 1 value is 1, 2 value is 1, 4 value is 1, 7 value is 1. Remaining all are 0. For example, here I place 1, 1, 1. Then I select input 7. This 1 is simply reaches to sum output. Your sum have 7 value. The same logic, if I place 0, 1, 0, then second input was selected. The second input value is 1, that is directed to sum output. It was there in your sum expression. In a similar way, carry also implemented by using 8 by 1 multiplexer. Here also selection lines are S2, S1, S0. My carry have minterm 3, 5, 6, 7. Only 3, 5, 6, 7 are ones and remaining all are zeros. Based on the combination present on this, either 0 reaches to output or 1 reaches to output. This is the way how we are realizing Boolean functions by using multiplexers. The next one is demultiplexer. Basically, demultiplexers can do reverse function of multiplexer. Your multiplexer have 2 power n inputs with 1 output along with n selection lines. But coming to demultiplexer, it has 1 input, 2 power n outputs. See here, friends, this is a 1 input. These are the 2 power n outputs with the number of selection lines are n selection lines. So this is a simple demultiplexer. And the functionality of demultiplexer is reversed to the multiplexer so that here based on the selection lines, the combination whatever the present over this, we select one of these output. This input was directed to that corresponding output. So that demultiplexers we generally call as data distributors. See here, only one output is connected to input based on the selection lines. Yes, absolutely. It is also called data distributor because we are distributing this input to among all these outputs. At any instant of time, we select one of these outputs. Its function is reversed to the function of multiplexer. Just now I told you. If I consider a simple 1 by 4 demultiplexer or 1 to 4 demultiplexer. So this is the block diagram of it, right? This is a block diagram of it. See here, this is a block diagram, data in and selection lines, the outputs Y0 to Y3. Based on the combination present on this D in is directed to I0 to I3. See here, friends, both are 0, 0. S1, S0, both are 0, 0. That means Y0 was selected. So Y0 is equivalent to D in and remaining outputs are 0. Next, both are 0, 1. Then we are selecting a Y1. So D in is directed to Y in. Remaining outputs are 0. Next combination is 1, 0 over this. Then we are selecting Y2. So then Y2 is equivalent to D in. Remaining outputs are 0. Last combination is 1, 1. Then we select Y3. D in is directed to Y3. So for implementation of this, so Y0 can be produced by an AND gate. So Y0 is equivalent to D in, right? So this is a data input and your selection lines are S1 bar, S0 bar. So this is S0 bar and this is S1 bar. So output is Y1. Whatever the value here we have at a data input, that is reaches to here. Next, Y1 is equal to S1 bar, S0, D in. So this is a D in. So this is S0 bar and this is S1. And the next case is for Y2. Y2 case, Y2 is equivalent to D in. When S1 is equal to 1, S0 is equal to 0. S0 0, S1 is equal to 1. And last case, Y3 is equal to D in. S1, S0 is equal to 1, 1. S0 1, S1 1 and D in. So output is 1, 3. So similarly, if you go for higher order multiplexers, demultiplexers also. So thank you for patient listening. We'll meet on you next class.